And okay, let's jump into it. So question one, we are asked to use the rational zero theorem, to find all real zeros of P of X. So think P's and Q's. Our constant at the end, we want to find our factor pairs of -6, so ±1, ±2, ±3, ±6. And then for our Q's, we have our factor pairs of the leading coefficient, which is 1, and so we just have ±1. So P over Q literally just gives us the numerator, since our denominator is ±1. And what does this tell us? This gives us all of the potential zeros for this cubic function. And so now we just want to take a guess. And I personally always start with 1 to see if that works. And then I go from there. So if 1 works, let's use our synthetic division. 1, 2, -5, -6. We don't have any placeholders here. Uh, 1, 2, -5, -6. And so we're going to bring the 1 down. 1 times 1 is 1. Take the sum, we get 3. 3 times 1 gives you 3. Take the sum, -2. -2 times 1, -2. That doesn't work. We need that remainder to be 0 for it to be considered a factor. So 1 doesn't work. But now let's try -1. Carrying out synthetic division again. Bring the 1 down. 1 times -1 is -1. Take the sum, we get +1. Product again, -1. Take the sum, we get -6. Ooh, we get that remainder to be 0. So we know that x plus 1 is a factor. Because x plus 1 is a factor, now we can look at what's left over. We have an x squared plus x minus 6, which we know how to factor quadratics quite well. This is just factored into x plus 3, x minus 2. And now we can very easily identify all of our zeros. In ascending order, we have -3, we have -1, and we have +2. And we're done. Kind of did everything in part A, because part B was saying using the result from part A, factor P of X completely. And so if we put it all together, we have our P of X is simply x plus 1, x plus 3, and x minus 2. Go ahead and move to the next page. We're given a stake is to be driven into the ground away from the base of a 50-foot pole. So I'm going to go ahead straight off the bat Draw in my 50-foot pole. And then we have a little stake here that is a certain distance away. A wire from the stake on the ground to the top of the pole is to be installed at an angle elevation of 60 degrees. So we want a wire to be installed at an angle of theta is equal to 60 degrees. Have a nice little right triangle at play here. And we're asked in part A, at what distance from the base of the pole should the stake be placed? Ooh, we're gonna have to use some trigonometry here. SOHCAHTOA, your acronym for sine, cosine, and your tangent functions, which are applied to right triangles. And so if we want to find out the distance from the base of the pole from the stake, we want to figure out what our adjacent side is. And we're only given our opposite side, which means we are going to be honing in on our TOA, which involves our opposite and our adjacent. Our tangent of theta is equal to our opposite side over our adjacent. So plugging in the values that were given, our tangent of 60 degrees is equal to 50 over x, and we want to solve for x. Now tan of 60, I'm going to put this off to the side here. Tan of 60 is the same as sine of 60 over cosine of 60, which is square root of 3 over 2 divided by 1/2, which gives you just the square root of 3. So now what we can do is we can substitute in that square root of 3 for tan of 60. Let's go ahead and cross multiply. We get square root of 3 times our x is equal to 50. And then let's divide both sides by that square root of 3. And so we get x is equal to 50 over square root of 3. And last but not least, we got to rationalize this denominator by multiplying by square root of 3 over square root of 3. So our x value is 50 square root of 3 over 3 feet. We're done. Part B asks us, what will the length of the wire from the stake to the top of the pole be then? So now we want to find the hypotenuse. But what special triangle is this? It's a 30, 60, 90. So yeah, you can use SOHCAHTOA again. Or you can also just use your properties of 30, 60, 90 degree triangles and their respective sides. So 30 is always opposite the shortest side. and the hypotenuse is always double the shortest side. So 2 times 50 square root of 3 over 3 gives you 100 square root of 3 over 3 feet, which is your hypotenuse. And we're done. Yeah. Why did I multiply by 2? Because in any 30, 60, 90 triangle, I'm really not drawing this to scale. I should really make the 30 more apparent. We have the ratios x, 2x, 2x, x rho 3. Let me write it down. X, 2x, and x square root of 3 in your 30, 60, 90. And so if you know the shortest side, then you know the longest side is just double that. So our shortest side is opposite the 30 degrees. So our 50 square root of 3 over 3. Our longest is just double that. You could also, if you wanted to, you can just do what we did in part A again, our SOHCAHTOA, and you just want to find the hypotenuse. So, for example, sine of 60 is your opposite over your hypotenuse, and then you just solve for your hypotenuse h, which is h is equal to 50 divided by sine 60, and sine 60 is square root of 3 over 2. So 50 divided by square root of 3 over 2. Keep, change, flip. And you get 100 square root of 3. Sorry, you get 100 divided by square root of 3. Rationalize the denominator, and you get the same answer that we got. So either way would work. All right, let's move on to question 3, which is a circle question. And so we're going to end up completing the square 2 different times here. So we're going to pair our x's together, create a little bit of space, pair our y's together, create a little bit of space, and then move that constant over to that right-hand side. Now let's use our special key. We're going to add 1 to both sides for our x. We're going to use our special key for our y, which is our b value is 6. Divide by 2, which is 3. Square it, you get 9. Add 9 to both sides. And so now we just put ourselves in a really good position so that we can easily factor our yellow and our blue equations. Our yellow turns into x plus 2 in parentheses squared. Our blue turns into y plus 3 in parentheses squared. And then that entire right-hand side, the 9's cancel out, so we get our radius to actually just be 1. And they don't even ask us for our radius and center point. They just ask us to write our equation in standard form, which we did. So this completes this question. Part B to this question is now understanding what the center point and the radius are so that we can graph it properly. So our center point is -1, -3, and our radius is the square root of 1, which is just 1. So when we plot this, -1, -3, we're just going, think of a compass, north, south, east, west, up 1, down 1, to the right 1, to the left 1, and then sketch in your circle. We're asked to label the center and the radius. So let's draw a little arrow to label that center point. And then I'm going to put R for my radius, so radius is equal to 1. And then we don't want to forget to write the equation of the circle. So x plus 1 squared plus y plus 3 squared is equal to 1. And then we're done. I'm going to go ahead and move on to page 4, which is dealing with a system of nonlinear equations. Lucky for us, they already have it in substitution format, right? We have that y isolated on the bottom. So wherever we see a y in that top equation, we're just going to substitute in 4 minus x squared. So we have 2x plus 4 minus x squared is equal to 1. Let's simplify. So we end up with negative x squared plus 2x plus 4 equals 1. And I'm actually going to bring everything to that right-hand side so that our leading coefficient is positive. And so we're looking at x squared minus 2x minus 3 equals 0. Now we can factor this into x minus 3, x plus 1, which tells us our two potential solutions for x are x is equal to -1 and x is equal to +3. Now let's create our t-chart in order to find those y values. And once again, our y is equal to 4 minus x squared. So we just want to find y when x is equal to -1 and when x is equal to 3. We have y is equal to 4 minus 1, which means one potential solution is at -1, 3. And then another potential solution is at y is equal to -5. The point 3, -5. So now let's check these. When x is -1, we get -2 plus 3. That works good. And then we get 3. Is that equal to 4 minus 1? Yep. So we're good for that first solution. Now let's take a look at that second solution. When x is 3, we get 6 minus 5 is 1. Good. -5, does that equal 4 minus 3? Nope, sorry. 4 minus 9. It does indeed. So that also works. So our two solutions are -1, 3 and 3, -5. Let's move on to part B, where we're actually asked to graph these two equations. So I'm going to write them down here so I don't have to keep scrolling. 2x plus y equals 1. And then y equals 4 minus x squared. So we're going to graph a line and a quadratic. So let's put this line into y equals mx plus b form. And when we do, we're looking at y equals -2x plus 1, which tells us we have a y-intercept at 1, and our slope is down 2 over 1. So we can plot a few points and then connect the dots. And then don't forget to write the equation of the line. Our second, we're dealing with a quadratic, but it's really y is equal to -x squared plus 4. So we have two transformations that take place. Know that x squared is an upside or a U-shaped parabola. It's upright. But -x squared, it's a reflection. It's flipped. It's upside down. And that plus 4, x squared stems from the origin, but that plus 4, we're doing a nice vertical shift up 4 units. So our new vertex here is actually going to be at 4, and then we're going to be going down. The sketch would be something like this, but we really should plot some points. We know the solutions, -1, 3 is an intersection point, and we know 3, -5 is also an intersection point. And if the vertex is on the y-axis, then we can just use our knowledge of reflection to create their symmetrical points. So 3 points over, we have a point here at -3, -5. And then we have a point at 1, 3. We should probably do our x-intercepts as well. So 4 minus x squared is the same as 2 minus x, 2 plus x, if we factored it. So that tells us we have -2 and +2 as our x-intercepts. And now we can plot out our parabola and then write our equation. It says clearly label the solutions. So I'm gonna just circle them. We have -1, 3 solution. And then we have 3, -5. And that's it. Yeah. Doesn't matter. Yeah. Right. We're going to move on to page 5, where we're now into some trigonometry. And we are asked to evaluate and simplify. So Don't forget about this cosecant in the beginning, but we're going to apply that later. Let's first hone in on maybe our inverse sine of 1/2, which is just telling us sine of what angle gives us 1/2, and that's just pi over 6, right? Sine of 30 gives you that 1/2. And then we have our cosine inverse function. Sine of what, or cosine of what angle gives us 1/2. And that's just 60 degrees, also known as pi over 3. We did a very similar question like this earlier, where we realized pi over 6 plus pi over 3 just gives us pi over 2. Now we can bring down our cosecant. Cosecant is just 1 over sine. Remember, it's always that s that's wedged in the middle. It tells us, oh, that denominator's sine. So 1 over sine pi over 2. And we know that sine of pi over 2 is just 1. So our final answer is just 1 in simplified form. Question 6. Looking at a difference quotient. So we have f of pi over 2 plus h. So wherever you see an x in our function, we're going to draw in our parentheses. So sine parentheses. And we're going to fill that with our pi over 2 plus h. And then we have minus f of pi over 2, which is just sine of pi over 2, all over h. So we're actually looking at difference of signs, right? Sum and difference formulas with that pi over 2 plus h. And I'll maybe write that general formula off to the side to recall your memory. We're dealing with sine, so the signs are going to stay the same. We have our sine of our alpha plus beta, but the pairings are going to be different. So we have is equal to sine of alpha, cosine of beta, plus cosine of alpha, sine of beta. And so we're going to let our alpha be equal to pi over 2 here. And our beta is going to be equal to h. So let us substitute it in now. We end up getting sine of pi over 2 cosine of h plus cosine of pi over 2 sine of h. Sine of pi over 2 is 1. Cosine of pi over 2 is 0, which will shoot this whole thing to 0. So essentially, we're just left with a cosine of h. And now we can plug that back in over here. And we get cosine of h minus, what is sine of pi over 2? 1. All over h. This is our simplified form. we're going to go ahead and move to the next page. Even and odd functions. It's a good review of even and odd. We want to determine whether this function is even, odd, or neither. So let's recall our memory definition of an even function is when f of negative x is equal to f of x. Definition of odd function is when f of negative x is equal to negative f of x. And anytime you're testing, you always want to start with the even. And if it's not even, then you go down to your odd. And if it's not odd, then you know it's neither. So third step, if 1 and 2 don't work, your function is neither. So let's proceed with the steps. Our original function is x plus the absolute value of x. And so f of negative x, wherever you see an x, you're just going to put in a negative. And then you're going to simplify. So we get this f of negative x is equal to negative x plus the absolute value of negative x is just positive x. Is this equal to our original function? So because this is not equal to x plus absolute value of x, our function is not even. And then we have to move on to step 2. So this was our first step. Step 2, we want to see if it's odd. So we're going to use what we have in yellow here, and we want to factor out a negative from our yellow. So factor out a negative from yellow. I'm not even going to say from yellow function. I'm going to just write it out from negative x plus x. And so when we do, we end up with negative in parentheses x minus x. And again, this is the same as our f of negative x. It's just we manipulated it a little bit. The reason why I factored out that negative is we want to compare it to our definition of an odd function. And so what we have in parentheses here is this equal to our original function? It's not, right? This is not equal to negative f of x. And negative f of x is the same as negative negative x minus absolute value of x. These two are different. Therefore, I'll just write our function is not odd. And therefore our function is neither. Any questions on this one? Yeah.
Testing for the negative f(x).
Mhm.
Why do you put a negative symbol in front of both x's as well, instead of just the entire function?
Why do I put it in front of, when you say both x's?
Like, see like the third line from the bottom, like purple letters, I guess?
Yeah, here?
Yeah, like, why is it not just negative parentheses x plus absolute value of x?
Oh, good question. So our negative of our original function is factoring out a negative value from our original function, but we want to keep it when we factor out we're keeping it, like we're not changing it, we're just manipulating it. We pull out the negative, but it doesn't change it. Like if we put the negative back in, we still get back our x plus. Yeah. Yeah. This is the reason why I did this was just to compare to really show you guys that what we have inside parentheses here, they're clearly not equal to each other, which means it's not odd. Yeah. If x minus x was equal to negative x minus absolute value of x, then it would be odd, but it's not. X minus x is 0, and negative x minus absolute value of x is the same as negative x minus x, which is negative 2x. Negative 2x is not equal to 0.
I'm still a little confused because isn't like negative f of x supposed to be a reflection? So inherently, would it be the same?
So that's the properties of even and odd functions. So even functions, look at this reflection that's taking place. Your input is negative x and it spits out your output, which means all of negative x values give you positive x values, aka a reflection across your y-axis. So definition of even functions are reflections across your y-axis, whereas definition of odd functions are reflections across the origin, which is a reflection across both your y-axis and your x-axis. Not y equals x. Y equals x is different than the origin. That's a very common mistake that students make. So y equals x flips your xy values. Reflection across the origin also deals with the negation of your x and y value signs. Yeah. Yep. Cool. Okay. Question 8. We have, suppose that f of x is a linear function, and we just want to find an equation of a line. So anytime you find equations of lines, think of, I need a slope, and if they give me a point, I can use a point slope formula. Cool. They give me 2 points. If it helps, we can write this in XY coordinate format. So we have a 1, 0 and a 2, 3. So we can utilize our slope formula, our change in y over the change in x, which is 3 minus 0 over 2 minus 1, which gives you 3 over 2. And then we want to use our point slope formula. Did I make a mistake? Thank you so much, Dorian. So yeah, our slope is 3. And so now using point slope formula, we have y minus y1 is equal to mx minus x1. Does not matter which point you use, but I personally like using the easier one. aka I'm going to make y be 0. So we have y minus 0 is equal to, our slope is 3, and then x minus 1. And then that gives us the ability to simplify it very easily. You could keep it in this form since they don't specify slope-intercept, or you can put it into slope-intercept to get y is equal to 3x minus 3. And there we have it. We found our equation of our line using 2 points. Go ahead and move on to page 7. I feel like they're going to ask us to graph this. Oh no, they're not. New question, question 9. Another double angle formula question. They really like to use sine 2 theta. Sine of 2 theta is simplified to 2 sine theta cosine theta, famous double angle formula. And we're asked to solve this equation for all values on the interval from 0 to 2 pi. So we're going to have some definite answers here. And so what I'm going to do straight off the bat, I'm going to sub in this 2 sine theta cosine theta for my sine 2 theta. So we get 2 sine theta cosine theta is equal to sine theta. And then I'm going to bring everything over to that left-hand side. So I'm going to subtract sine theta from both sides. And so when I do that, I have now 2 sine theta cosine theta minus sine theta is equal to 0. We can factor out a sine theta from each term. And so we get sine theta in parentheses, 2 cosine theta minus 1 is equal to 0. And now we can set these values equal to 0. So we have sine theta set equal to 0. And then we have 2 cosine theta minus 1 equal to 0. With the 2 cosine theta minus 1, if we add 1 to both sides and then divide both sides by 2, we're essentially looking at cosine of theta is equal to positive 1/2. And so now this is where looking at our circle, our unit circle, knowing where our trig functions are positive and negative, and finding all of our possible values. So the first one, sine theta is equal to 0. That just tells us where are points lying on our x-axis. And we're including, right, all theta values between 0 and 2 pi and including 0 and 2 pi. So it's actually 0, 2 pi. And then what's this value on that left-hand side? Pi. It doesn't even have to be, it's not negative 2 pi because that doesn't lie in the bounds. It's just 0, pi, and 2 pi give you 0 if you plug theta in for those. So we have theta for our sine. It's just 0, pi, and 2 pi. There are solutions for that case. And now let's figure out, okay, what are all of our solutions that give you cosine theta to be 1/2? Well, It's positive. So we want to look at the quadrants that make cosine positive. First quadrant and last quadrant. And 1/2. What angle measure are we dealing with here? Pi over. Good. So our reflection, or not reflection, our reference angles in these quadrants are going to be at pi over 3, aka 60 degrees. So we have one here, and we have one here, which means we're looking at our pi over 3. And we're looking at, well, what is 2 pi minus pi over 3? Good. So our two solutions for our cosine side is pi over 3 and 5 pi over 3. So we have 5 solutions in total. In ascending order, we have 0, comma, pi over 3, comma, pi, comma, 5 pi over 3, comma, 2 pi. And we're done. Let's zoom out. Question 10 deals with a cofunction identity, that tan 90 minus a. So let's solve this. 90 degrees is the same as pi over 2. So we can look at this as tan of pi over 2 minus a, if that looks familiar. Or if you know tangent is sine over cosine, this is the same as sine of pi over 2 minus a over cosine of pi over 2 minus a, which may look even more familiar because we know the cofunction identities tell us that this is the same as just cosine of a over sine of a, also known as cotangent of a. So we can really replace that tan of 90 minus a with our cotangent of a, or just a cosine a over sine a. We're going to have to eventually put it in terms of cosine and sine so that we can cancel out some stuff. So I think that's what I'm going to do. I have cosine a over sine a in my numerator, all divided by cosine a sine a, and as that as a fraction is just over 1, because we'll utilize our keep, change, flip. And when we do, that's the same as cosine a over sine a times 1 over cosine a sine a. Some of this. So now you can see, for multiplying straight across, well, we have a cosine a in the numerator, and we have a cosine a in the denominator. And then we have 2 sine a's in the denominator, so that can be simplified to 1 over sine squared a, also known as cosecant squared a, which is simplified form. and we're done. All right, so now we're on to our question 11, which is going to utilize our theta is equal to our S over R, S representing the length of the arc and R representing the radius of a circle. So I'll highlight these accordingly. And what you really need to remember for these types of questions is the fact that your theta needs to be in radians every single time. And so we're really just plugging in for our respective colors and then solving for the missing variable. So we have our theta here. We have our R. We have our S. We're trying to find our R. Okay. And so I'm going to go ahead and cross multiply. We're dealing with a lot of fractions here. So when you cross multiply, I would actually make sure that you don't switch up the numerator and denominator. I'm just going to do 3 over 2 times R is equal to 33 over 5. I don't want to confuse you with these butterfly wings. Maybe I'll make them a little larger. And now let's divide both sides by 3 over 2. So we're going to utilize our keep change flip here. My pen's not working. Oh, there it is. And so we're looking at R is equal to 33 times 2 over 3 times 5. And before we multiply straight across, we can do some simplification. 3 goes into 33 11 times, and 3 goes into 3 once. So this just reduces to 22 over 5 for our radius, and we're done. Radius is equal to 22 over 5. Let's move on to question 12. We have if tan A is equal to 4 over 3, well, 4 over 3, 3, 4, 5, Pythagorean triple. So what does that tell us about sine A? Well, TOA, opposite over adjacent, so opposite over hypotenuse, that gives us 4 over 5. And then cosine, adjacent over hypotenuse, that's just 3 over 5. Then we're given sine of B is equal to 12 over 13. Ooh, another Pythagorean triple. That's a 5, 12, 13, right? 5 squared plus 12 squared. 25 plus 144 gives you 13 squared, gives you 169. So now we can figure out cosine of B. If our hypotenuse is 13, then our other side by Pythagorean theorem or by our Pythagorean triple is 5. So we get 5 over 13. We don't have to do the tan of B since we're dealing with sums. It's only sine and cosine. But We do want to read the entire instructions because it does say angles A and B are in quadrant 1, which doesn't affect anything. Everything's positive. But if that quadrant number was different, we would have to put in some negative values. So just be on the lookout for that on the final exam. Now we have this cosine of A plus B. And let's go ahead and write out our sum of cosines formula. Put it in black so you could see it more clearly. So our cosine, cool thing about cosine is the fact that the pairings are the same, but now the signs are different. So we get cosine A plus B is the same as cosine A cosine B minus sine A sine B. Now we're just substituting in. So we have cosine A, which is 3/5. Cosine B is 5/13. Minus sine A is 4/5. And sine B is 12/13. Simplify and we get 15. We know the denominators in both cases are going to be the same, 5 times 13. 10 times 13 is 130, so 5 times 13 gives you 65. And then we have 3 times 5 is 15, and then 4 times 12 is 48. So 15 minus 48. So our final result ends up becoming 33, negative 33. Yeah. I think my brain is slowly shutting down. And we're done. That's in fully simplified form. Let's move on to question 13, which is a nice, straightforward distance formula. Take a little breather here. Oh, not distance formula, midpoint. So it's important to read. And so when you're finding the midpoint, you're finding the average of your two x values and then the average of your two y values. So your midpoint formula is just x1 plus x2 divided by 2, comma, y1 plus y2 divided by 2. We have our x1, y1 and our x2, y2. And so we're looking at -2 plus 6 all over 2, comma, 4 plus 2 all over 2, which gives us 4 over 2, comma, 6 over 2, which reduces to 2, comma, 3. I'm going to go ahead and move on to question 14. Yeah. Solve the logarithmic equation where we have log base x plus 3 of this whole expression is equal to 2. And so straight off the bat, I am going to convert this into exponential form. And then another thing to just highlight is they're helping us out here. Do not check for extraneous solutions. So once we find our values of x, we're done. We can move on, which is great. Let's convert this into exponential form. And so what we're looking at is x plus 3 raised to the second power is equal to everything we have in parentheses here. So x plus 3 raised to the second power is equal to this whole mumbo jumbo. And now let's factor out that left-hand side. So we're looking at x squared plus 6x plus 9 is equal to our x to the third plus x minus 2 all over x. And now what we're going to do is we're going to cross multiply. And so we get x times our x squared plus 6x plus 9 is equal to x to the third plus x minus 2. No longer dealing with any fractions. Now let's use distributive property, and then we might be able to combine some like terms. X to the third plus 6x squared plus 9x is equal to our x to the third plus x minus 2. And let's bring everything over to that left-hand side. So I'm going to subtract x to the third from that right-hand side. I'm going to subtract x from that right-hand side. And then I'm going to add 2. Let's shrink this a little bit. And so now the x to the third minus x to the third cancels out. So we're really just looking at 6x squared, and then 9x minus x is the same as 9x minus 1x, which gives you a plus 8x. Plus 2 is equal to 0. I'm going to bring this up over here. And now we can utilize our AC method to factor. What are factor pairs of 12 that add to 8? 6 and 2. We're going to keep that first and that last term the same. And then we are going to manipulate that 8x into a plus 6x and a plus 2x. And now we can utilize our factor by grouping. The first two terms, we can pull out 6x, and when we do, we're left with x plus 1. And then the last two terms, we can pull out a 2, and when we do, we're left with x plus 1. And if we did factor by grouping correctly, what we have inside the parentheses should be exactly the same, and they are. So we're now going to factor out our yellow x plus 1. And when we do, we're left with 6x plus 2 in that other parentheses. And now we can find our values of x. Just set them both equal to 0. One potential solution is x is equal to -1. And then the other solution, we have 6x plus 2 is equal to 0. So 6x is equal to -2, which means x is equal to -2 over 6, also known as -1/3. In the instructions, they did not ask us to check. So we're done. X equals -1 and -1/3. Any questions on this one? I feel like the hardest part was converting it into exponential form and then making it into just the numerators, or not numerators, just getting rid of the fractions. Once you got to this stage in black over here, it was more just down to algebra and factoring again. Yeah.
It's kind of the whole thing, but like, I understand logarithms and all that first step stuff,
Yeah.
but like, I don't know how to use the AC method.
AC method. Okay. So no, good question. AC method. It's going to be there. It's important to know. But I'm glad you asked. So AC method, remember when you're looking at any quadratic function, it's in the form of ax squared plus bx plus c. So our AC method, AC is just you're taking the product of your A value and your C value. 6 times 2 gives you 12. And then your B value, I just want to make sure I'm not reusing colors. Okay, my B value, can use blue here, is 8. And so what you essentially do is you always just want to ask yourself, what are factor pairs of that top number in our X? So factor pairs, what two numbers multiply together? 1 and 12, 2 and 6, 3 and 4. So I can write that off to the side. Factor pairs of AC, which is 12. We have 1, 12, 2, 6, 3, 4. These are all of them. Obviously, you can manipulate using negatives, but all of our numbers are positive here, so we don't have to worry about that. What are factor pairs of 12 that add to 8? 1 plus 12, that's 13. That doesn't work. 2 plus 6, ooh, 8. And 3 plus 4, that gives you 7. So that's how we know that it's 2 and 6. So, yeah. And then do you get this part down here?
Oh yeah.
Yeah, okay, cool. All right, let's move on to question 15, where we're just asked to use this graph in order to find the range. So all of our possible y values are what?
Infinity.
Be careful.
6 to beta 6.
Well, remember, we're looking at both of these graphs represent the function. So yeah, the only exclusion, what's the only restriction? X can't, or its range, y can't be equal to 0. X can't equal 0 either for the domain because we have horizontal and vertical asymptotes at x equals 0 and y equals 0. But they're specifically just asking you to find the range. So yeah, our only restriction is y can't be 0, which means, yeah.
Well, there's no arrows, so it doesn't the graph player.
Oh, clever. Yeah, there are no arrows. So, because there are no arrows, yeah, we have more restrictions, right? Y can't be less than -6, and then y can't be greater than +6.
Also, but also by the horizontal asymptote, there's no arrows, so it ends at -1/6 and 1/6, not at 0. You know. Like it's not going to the size.
Yeah. Good. Really good observations. Really good. Okay, so we have 1/6 and -1/6. So if we were to write this in interval notation, now what would we have? Hard bracket, -6 up to good, good, union, +1/6, all the way up to, you got it. Great. We weren't going to include the 0 regardless. That's our horizontal asymptote, but the biggest thing is there's no arrows anywhere on these functions. So it's not even just the lowest. We want to look at what the lowest possible value is, which is at y is equal to 1/6 for this part of the function, and then y is equal to -1/6 at this part. So anything between -1/6 and 0, and between really anything between -1/6 and +1/6, that's a restriction. So I can write this up here. Y is not equal to any value between -1/6 and 1/6. Yeah. Can you erase this part? Cool. Let's move on to question 16, which is a composition of functions. And so we're first going to evaluate f of -3. And so when we do, we get -3 in parentheses squared minus 6, which gives you 9 minus 6. And 9 minus 6 gives you 3. And now let's evaluate g of 3, because f of -3 is 3. And so wherever you see an x in your g of x function, you're going to replace it with 3. 2 to the third is 8, and 8 minus 1 gives you 7. So our answer of g of f of -3 is just 7. There'll always be at least one composition of functions question on the exam. Okay. Let's move to question 17, where we're given f of x, we want to find the inverse, and we want to state the domain and range of the inverse. So how do we find inverses of functions? Yep, so we have y is equal to x squared minus 6, but we want to swap it now. So we have x is equal to y squared minus 6. Isolate your y, so we get y squared equals x plus 6, and then take the square root of both sides. So we're looking at y is equal to the square root of x plus 6. And put in proper inverse function notation. F inverse x is equal to the square root of x plus 6. Really honing in on that positive one, because we want to make sure that it's a one-to-one function when we take the inverse. We restrict that domain. Okay, now we're asked to state the domain and the range of our inverse function. Well, the domain of our inverse function is quite straightforward, right? finding domain, look for two restrictions. Denominator can't be 0. Don't have to worry about that here. And then the second condition is underneath your even roots have to be greater than or equal to 0. So set x plus 6 to be greater than or equal to 0, and you get your domain to be greater than or equal to -6, which is just -6 up to infinity in interval notation. Whereas the range, what's that cool trick? The range is the same as the domain of the
inverse.
Yeah. The range of the inverse is the same as the domain of the original. The range of the original is the same as the domain of the inverse. And so that's another way to look at it too. You know that this domain, this inverse function is correct because the range of this quadratic x squared with a vertical shift down 6 units also tells us that our range is -6 to infinity, which is the same as the domain of the inverse. Okay, so now let's find the domain of x squared minus 6. And what's the domain of that? It's just all real numbers, right? I'll graph it here. So we get all real numbers, -infinity to infinity, and we're done. We just have to put that in to our answer key down here. So we get square root x plus 6 for our inverse, our domain, -6, I'm losing my voice, oh my gosh, -6 comma infinity, and then range -infinity comma infinity.
Oh, that is so perfect.
Yeah, thank you. Cool. So questions 18, 19, and 20 are all graphing ones. I guess we can do these really quickly. They won't take too long to just do from scratch. We have our r of x is equal to x plus 2 over x minus 3. So you immediately want to think of the parent function where you're going to have something look something like this. Okay. A lot of students on quizzes only did one side, so just make sure you're including both of them. But the biggest thing is really identifying your x-intercepts, y-intercepts. They're asking you to just sketch these graphs, so we're keeping it very vague here. But x-intercepts, y-intercepts, and then your horizontal and vertical asymptotes. So our x-intercept is just when y equals 0. So we get 0 is equal to x plus 2 over x minus 3. And we just set x plus 2 equal to 0, which means our x coordinate is -2. So we get -2 comma 0. And then our y-intercept is when x equals 0. So we plug in a 0 for wherever we see an x. And we get y is equal to -2/3. So our y-intercept is 0 comma -2/3. So let's plot those. We have -2, 0, And then we have 0, comma, negative 2/3. Okay. Now let's put in our horizontal and our vertical asymptotes. Vertical asymptote is just what makes the function undefined. So when x is equal to 3. And then our horizontal asymptote, think about the end behaviors, but also think about the trick that I told you. It's just if the highest degree in both the numerator and denominator is 1, then it's just the division of the coefficients. So 1 divided by 1 in front of our x's is just 1. So your horizontal asymptote is just y is equal to 1. And let's graph that. So y equals 1. I'm going to put those as a dashed. And then x is equal to 3. You have to label them. Make sure you get that full credit. So x equals 3, y equals 1. And now, again, it's a sketch, so we can just sketch it out at this point. I think my hand is just so tired. Try one more time. Right, that's good enough. Okay, it says label the asymptotes, we did, and the intercepts. So we gotta, this is our x-intercept, which is negative 2, 0. And then this is our y-intercept, which is 0, negative 1. Last but not least, don't forget to write out and name your function. R of x is equal to x plus 2 over x minus 3. That's it. Full credit. Yeah. The y-intercept. Yeah, negative. Oh, thank you. Thank you. I graphed it properly. I just wrote it wrong. 0, negative 2/3. Great, thanks. I like creating these videos with you guys because you catch my mistakes. So when I do them on my own and I catch the mistakes later, I have to make the video all over again. Yeah, yes.
From like x equals 4 and then plug it in. Like x.
Yes, you can. If you put x equals 4, then you get 4 plus 2, which is 6 over 1, and then, yeah, 6, 1. Yeah, and you can plug that in. Yes, definitely. I recommend you doing that, actually. Pick good x values that you can divide, and then you can easily plot.
Wouldn't it be 6, 4? I mean, 4, 6.
Oh yeah. 4, 6. Good, yeah. Thank you. All right. Let's move on to page 12, question 19. We're dealing with a piecewise function here. And we have a linear function and a root. Remember that square root of x looks something like this. And this linear function has a negative slope and then that y-intercept of 2. So what I personally think you should do anytime you're dealing with piecewise, create a table and choose good values. So we have all values of x less than 0, which means I'm going to put 0 twice. I'm going to put 0, and then I'm going to have 0 at the whole, and then 0 at the function it's being included in. And then I'll pick a few values less than 0. Let's pick -1 and -2. Should be more than enough. Let's pick some values greater than 0, but be careful because greater than 0, we're dealing with the square root. So we want to pick perfect squares to make our numbers nice and clean. So let's pick 1 and let's pick 4. And now we're just going to plug in. So -2 times -2 is a +4, plus 2 is 6. Then we have -2 times -1 is a +2, plus 2 is 4. And then we have a whole at 0 plus 2, which is 2. Now let's go on to that bottom equation. We have the square root of 0 is 0. Square root of 1 is 1, and square root of 4 is 2. So now we're ready to plot -2, 6, -1, 4, and then whole at 0, 2. So this is our linear part of the function. And then we have 0, 0, 1, 1, and 4, 2. And this is our root part of the function. Last but not least, let us write in our function and label it. H of x is equal to our -2x plus 2 when x is less than 0, and square root of x when x is greater than or equal to 0. And that's it. Question 20 is an absolute function graph. Keep this up in case you need to still see it. Absolute value of x is just that V-shaped, which I'll put off to the side so you could see. Y is equal to absolute value of x. And then we're looking at some transformations that take place. We have a horizontal shift, 1 unit to the, good. A vertical shift, 2 units down, and then a reflection across our x-axis. Beautiful. So think about it's going to be going to the left, down, and flipped over. That's what it's going to look like when we plot it. That horizontal shift and that vertical shift tells us where our new vertex is. Our new vertex is where? I'm going to go ahead and plot that. And then we just have that same slope. 1, it's just going to be upside down. So yes, you can do the table of values, or you can just go down 1/1 each time. And then you have your function. And then don't forget to label it. So we have our f of x is equal to negative absolute value of x plus 1 minus 2. And we're done. Almost there. Good. All right. Last question, guys. Question 21. Very similar to that sample exam. And I know it says it's only worth 4 points, but it is going to be worth 10 points on the final exam. So if anything, this is the question to study. Part A is, you had a question? No. Part A is asking you to find the amplitude. And so our amplitude is our absolute value of -2, which gives us +2. Our period, since we're dealing with cosine, our period is 2 pi over our absolute value of b, which is the same with sine. And so we need to find our b value. So how do we find our b value? We actually have to factor out, between both of these terms, we can factor out a pi. We can rewrite our function as -2 cosine of parentheses pi parentheses x plus 2, where we can very visually see our b. Let's think about this as a cosine b x minus c plus d. C is our horizontal phase shift. D is our vertical shift, aka also the equation of our midline. A is our amplitude, and B is used in order to find our period. So our B value is pi. Now that we know that, we can plug that in and find our period. The absolute value of pi is just pi. And so we end up getting 2 pi over pi, which is just 2. Now we want to find the horizontal phase shift, which, lucky for us, since we already factored everything out, we know our horizontal phase shift is 2 units to the left. Finally, we are asked to sketch one complete period of the graph along the interval they give it to us, -2, 0. So what we can do is I'm going to put in 0, negative. I don't want to go up by halves. So let's do -1/2. -1, -3/2, and then -2. Let me move these over a little bit though. And then create your table off to the side. So you already chose your x values. You have 4 good x values here. We'll plot our midline in a second, which, knowing that there's no vertical shift, what is our midline? Yeah. Put that in now. Okay. And now let's figure out our y coordinate points. So we have 0, -1/2, -1, -3/2, and -2. And I'm going to write my equation down here too. I'll just copy and paste this part here. I'll zoom in. Okay. So when x is 0, we have cosine of 2 pi. And cosine of 2 pi is, sorry about that, is 1, right? I'm going to put off to the side my circle too. I know my sheets keeps moving. I promise it's not me. It's the iPad doing stuff. Right. Cosine of 2 pi is just 1. And so we get this whole thing ends up being 1 times -2 gives you -2. What about -1/2? -1/2 plus 2 gives you positive 3/2. And then we get 3 pi over 2. 3 pi over 2 ends up over here. And what's cosine of that? 0. And so this whole thing goes to 0 times -2 is 0. -1, -1 plus 2 gives you 1. Cosine of pi gives you 1. Just remember the unit circle where everything is in terms, your x comma y is in terms of cosine theta, comma sine theta. And so in coordinate form, we have 1, 0 here. 0, 1, because it's a unit circle. We have -1, 0. And we have 0, -1. And we're only looking at the cosines, which is your x-coordinate point. These angle measures, right, over here is 0 and 2 pi. Up here is pi over 2, aka 90 degrees. Over here is regular pi, and then we have 3 pi over 2 down here. So I know we did this one, but I forgot what I said. Cosine of pi is -1. And so we get -1 times -2 gives you +2. Good. -3/2 plus 2 is the same as -3/2 plus 4/2, which is 1/2. Cosine of pi over 2 is just 0, which shoots everything to 0. And then finally, we have -2 plus 2 is 0. Cosine of 0 is +1 times -2 gives you -2. So let's plot these now. Along my y-axis, I'm going to now put in the scale of 0, 1, and 2. And -1 and -2. Okay. And so we have 0, -2, plot that point. -1/2, 0, plot that. -1, 2. -3/2, 0. And then -2, 2. So when we connect these dots, we'll end up with something like this. And then we don't want to forget to write the equation. F of x is equal to -2 cosine of pi x plus 2. And that's it. We're done. So this completes the final exam, sample B.